Okay, so welcome everyone to this new series of Quantum Spain seminars. And today I have the pleasure to introduce Mar Tejedor, who is also one of my closest collaborators recently. So she's a computer scientist graduate from the University of Delaware, and she also holds a master in computer science with a specialization in machine learning from Georgia Institute of Technology, and recently a master in quantum science and technology from University of Barcelona that he's about to finish this year. She is also a researcher at the Barcelona Supercomputing Center in quantum HPC applications under the group of workflows and distributed computing. She focuses on advances in the frontiers of quantum HPC by developing cutting-edge algorithms and integrating quantum computing resources with traditional HPC systems, as I believe that today will present to all of us. So welcome, Mar, to these Quantum Spain seminars, and the floor is yours.
Thank you so much, Alba. And I guess the introduction is done, so I'll start with the presentation. And basically here what I'm going to present is Qdislib, the library that we designed to implement circuit cutting in a hybrid environment. And first of all, so when I started with this problem, one of the first problems that they presented to me was this problem with having big circuits, but small quantum computer chips. So basically, how we would handle if a circuit was much bigger than in our case, our 5-qubit chip that we have in the BSC, the Mare Nostrum Mono, and how would we handle this? The second problem is that we have multiple powerful resources. As we know, in BSC, we have Mare Nostrum 5, which is a huge supercomputer with CPUs, GPUs. We also have right now a Mare Nostrum Mono, which is the first quantum computer that we have here at BSC. Right now, we have a 5-qubit chip, and also it's gonna about to start working the 10-qubit chip. And also we have access to other quantum computers resources like the EVM cloud, which we managed to get some credits and access. So our second question was more about how can we take full advantage of all of them and use it to simulate these bigger circuits that maybe in our Mare Nostrum Mono couldn't fit or whatever. So here is where we presented our solution, distributed quantum circuit cutting. This is the paper that we just released last month. It's called Distributed Quantum Circuit Cutting for Hybrid Quantum Classical High Performance Computing. And it comes along with the Qdislib library. This library is where we integrated everything we did about distributed quantum circuit cutting. It is a Python library. It's easy as installing pip install Qdislib. And it's used along with QPUs that I'll explain a little bit more what it is, but it's the framework that allows us to parallelize and make sure we take advantage of all these resources that I mentioned before. So before getting into detail in the theory, I'm going to explain what is PyCOMPSS and what we do with in workflows with PyCOMPSS. Basically, PyCOMPSS is a sequential problem but parallel execution. It allows us to define functions as a task, as we see in the example. And when we define a function as a task, we're telling the computer that this function can run in parallel along every time is called. And this allows to have this parallelized code that takes advantage when we have much resources than just like a regular laptop. Basically, it's based in Python, and it's better for integration of HPC, AI, and big data. And it's an agnostic computation platform, which means that we can use it in cluster, clouds, and cluster containers. A little bit of the runtime. It is a runtime deployed as a distributed master worker. Basically, we have a master where we run the application, and this master is in charge of sending this task, this function, this computation that we define as task to the multiple workers and make sure we can distribute it as best as possible along every resource we have. The sequential execution that starts in a master node and the tasks are offloaded in the worker node, as I said, and all data scheduling decisions and data transfers are performed by the runtime. So the user doesn't have to manage all this. One thing important is the task dependency graph that we see in the diagram. This is every node of this diagram represents a task that all the tasks that are like as a tree means that they can run in parallel, and that's going to be important in our case because we'll see it how we do it in the Qdislib. And basically, this diagram explains a little bit more in detail how PyCOMPSS is in charge of doing all this orchestration. Then, going a little bit more into the theory detail, what are the circuit cutting algorithms? Basically, they are techniques that partition quantum circuits into a smaller independent subcircuits that can be executed separately and then recombined to obtain the original circuit output. In this case, we're able to reconstruct the expected value of the original circuit. So if we have a 10 qubit circuit, we want to calculate the expected value. We can apply circuit cutting, measure smaller circuits, and then recombine and obtain the original circuit expected value. There are two techniques, wire cutting and gate cutting. And why are we interested in this? Basically, because with PyCOMPSS, I already mentioned, it is fully parallelizable, and then we can take advantage of all these resources that I mentioned at the beginning. So more in detail, wire cutting. In wire cutting, we split the quantum circuits by cutting by cutting wires between gate dependencies, and are executed in separately and then recombined, as I mentioned. In the wire cutting case, we generate 8 subcircuits by every cut. The top part, we measure the expectation value of the Pauli observables. In the bottom one, we initialize the cut wire with the eigenstates of these Pauli matrices, and then we have some coefficients to make this mathematical formula to be able to reconstruct the original expected value. But basically, the main idea is the wire cutting scales exponentially, 8 to the k, being k the number of cuts. Here in this diagram, we can see more detail on how this translates to define the combination of the circuits. And then we can go to the gate cutting. In this case, we use a technique based on quasi-probabilistic gate decomposition, which means that we partition a 2-qubit gate into a weighted sum of local operations and intermediate projective measurements. As in the example in the picture, a control Z can be cut in 6 subcircuits, and the resulting subcircuits are all of 1-qubit gate, which means it allows us to split this 2-qubit circuit into 2 1-qubit subcircuits. In this case, the scales exponentially within the number of cuts 6 to the k, which we see it's a little bit better than wire cutting. And we're going to focus a little bit more on this than wire cutting. So how does circuit cutting is implemented in Qdislib? Basically, this is the workflow. We have two key points. The first one is the graph-based approach for circuits. And when we get the quantum circuit, we convert it into a direct cyclic graph. Then we perform the wire or the gate cutting in this DAC form, generate all the combinations. And when we have all the combinations in parallel, we are converting it back to circuits. And then the second main point is the distributed resource constraint execution. That means that each of these subcircuits that are totally independent and can be run in parallel, we decide where to send it, either CPU, GPU, QPU, depending on the workflow, the user, or whatever is defined. After the execution, the values are grouped together, reconstruct using the formula, the theory formula, and the expected value of the original circuit is obtained. Here we can see a little bit more detail of the task-based graph that I said before. Here we have 1, 2, 3, 4, 5, 6 blue nodes, which means that we are performing a gate cut. Since, as I mentioned before, for each cut we obtain 6 combinations. And in each of these combinations, we have the top part and the bottom part that are also independent and that can be run independent. And here we can see in each blue node, we have 2 multiples white nodes. And this is like this sequential order of the tasks that are run totally independent and totally parallel. Yeah. At the end, the pink nodes are the expectation value calculation of each subcircuit, and we have this reduce task that groups all together and creates reconstructs the original expected value of the circuit. And here we have already some results that we published in the paper. These results are run in the Mare Nostrum 5 GPP, the general purpose partition. And there's a lot of information. I'll go step by step. First of all, here we're running hardware efficient ansatz that has this type, like this shape of two layers of rotational gates, and then all the qubits in cascade, like connected with 2-qubit gates. And what we can see is we have three different circuit examples: 32 qubits, 64 qubits, and 96 qubits. Obviously, as we have more qubits, it is slower. But the important thing is that in each of these cases, we are applying 4 cuts, which means that the circuits are split in four subcircuits of, in the case of 32 qubits, 8 qubits each subcircuit. The 64, 16 qubits each subcircuit. And in the 96, it will be 28 qubits each subcircuit. So what we're running here is 5,184 subcircuits in its for doing the simulation and being able to reconstruct the expected value of the original circuit. This is to understand why is it important for us to parallelize these executions. Like, you're running 5,000 subcircuits, and if we wouldn't have this parallelization, it would take like so long. Also, here in the graph, in the left one first, we have the Mare Nostrum node. That means how many resources, like how many nodes we have to execute each of each example. As we can see, and one of the most important part on our paper was seeing that every time that we were increasing, like doubling the number of nodes that we have, the execution time was cutting by half. We can see that in the right graph, that the execution time, every time we double the number of Mare Nostrum nodes that we're using, the time is cut by half, having a total speed up of 64.4, and like the perfect speed up will be 64. So it's pretty close, and that means our application scales really, really good. And this can even go farther if we had more nodes or even like bigger circuits. We're gonna talk about this a little bit later. Then we did the kind of the same in the Mare Nostrum 5 ACC using GPUs. First of all, I'm gonna focus on the first two graphs and then explain the last one. The first two graphs, we use the same circuit, the hardware efficient ansatz, but we have two completely performances. The first one, we have 64 qubits. 4 cuts, that means 16 qubits per subcircuit. And we can see that the GPU is much slower than the CPU. First of all, we have to remember that in a Mare Nostrum node, we have 4 GPUs against 112 CPU cores that will have a regular GPP node. That means that obviously, if the circuit is not big enough, the GPU doesn't have like this trade-off of using GPUs, which means it's much slower. Like, these 4 GPUs are not don't take advantage enough, and because the circuit is too small. When we go to the second case, where the circuits are much bigger, here we have 96 qubits cut in 4 pieces, each piece 28 qubits. We can see that the GPUs take much more advantage here, and that is much faster to do it in GPUs than CPUs. Here we wanted to point out how important is to acknowledge what are your resources and when do you want to send something to CPUs, to GPUs. At the end, one of our purpose was understanding our resources and using in the best way all of them. So in this way, we were able to understand and see what were the constraints in order to send something into a specific resource. Here and then after this example, we have the third graph. Here we use the random circuits inspired by the Google quantum supremacy circuit. The topology of this circuit is, as shown in the right side, is this mesh of 36 qubits. And what we wanted to do is apply a 5-cut in order to split this mesh into two different parts. Each one is 18 qubits, if I'm not wrong. Here, the circuit is much more complex than the regular hardware efficient ansatz. And as we can see, the GPUs also take advantage of having these bigger circuits and more complex, and it's much faster than the CPUs. One thing to note in all the graphs is that as we increase the resources, as we increase the number of nodes that we use, we're able to match the execution time of CPUs and GPUs. That shows us how good the application is able to use all the resources, and that even if in GPUs can be faster when we only have 1 or 2 nodes, if we're able to increase that in terms of CPUs, we can manage to have the same efficiency. And that's something that we can also play around, and it's very good for us because it's telling us that there is parallelizing and distributing in a really, really good way. After that, in the Qdislib, we also define find code function where we wanted to help the user find the best cut or find what is the cut that aligns more with the user's constraints. Basically, is that also a parallelized optimization function that computes the best possible cut attaining the user parameters. Pretty similar to the gate cut and wire cut workflow, we have a quantum circuit, we convert it to a graph. We have 2 different types of graph depending in wire cut and gate cut. We apply 4 different graph theory algorithms. Each one of these algorithms give us something a little bit different. For example, the Kernighan-Lim partition tries to minimize the edge swaps, the Gibbon-Newman cut in the high centrality edges. The spectral decomposition uses the Laplacian clustering, and the METIS is a multi-level coarsening plus refinement, but it's very, very good for meshes, which is a type of circuit that is very common, like we saw in the random circuits. Each of these graph theory algorithms give a type of cut, like a specific cut that we can apply in our circuit. Then we have the minimum loss function that scores all these cuts and finds the one that is less in the score. So it's like the best cut that these algorithms are giving us. We're going to end with the best wire cut and a best gate cut. We're going to do a minimum between these two, and we obtain at the end the best cut for that specific circuit. We also have the user parameters that we're going to tag now. As I mentioned, the optimization strategy, we have the loss function. In this loss function, we have trying to minimize the number of cuts. So the minimum number of cuts possible, the maximum components possible too, more independent circuits, subcircuits as possible. And finally, the minimum qubits possible too. So if we can try to get subcircuits of 2 qubits, better than if they are 5. Then we have these parameters that I was talking about. The user can specify, okay, I want all my subcircuits to be maximum of 5 qubits. Since then, I want to send all of them to the QPU that is only 5 qubits. Then the user can specify max qubits 5, and the function is able to find these constraint results. We have the same for the maximum number of components to restrict the number of subcircuits generated, the maximum cuts to restrict the maximum total number of cuts. Like I only want to apply maximum 3 cuts, give me the best option with that. It can do that too. And also enable or disable the cutting strategies. If I want to say I only want to find gate cuts, we can set wirecut to false, and that can be done too. And then we get the output, returns the best gate or wirecut. That is like the lowest score for that specific circuit using these graph theory algorithms. Here we compare our fine cut function, the Qdislib, versus what IBM offers using the Qiskit add-on. And this table that has a lot of results. I'm gonna just focus putting max qubits to 15. So I'm forcing to find results where all the subcircuits are maximum 15 qubits. And as we can see, we managed to get better results with the number of cuts. So we were able to find with the same circuits cuts with less number of total cuts. Yes. And then also we managed to do it faster. So these were really good results for us. Yes, mention also that this experiment was done with the random circuits that I mentioned before, the meshes ones that were obtained from the Google supremacy circuits and adapted to our specific case. Okay, now how we managed to do these hybrid executions with the Qdislib. We have the general hybrid workflow that I already mentioned. We have initial circuit. We are able to split it. Then we can do whatever we want with these pieces, these subcircuits. We can send it to a supercomputer or a cluster to do simulation in CPU or GPU, or we can send it to execute it on a site or on a cloud quantum computer. We have then after all these executions, we have this reconstruction phase that is going to be done in a CPU, and that's going to enable us to get the expected value of the initial circuit. Then down in the figure in the right, like on the bottom of it, is the VSE specific example. So we have some constraints that I'm going to explain, but basically the user is able to send the initial circuit into the general purpose partition in Mare Nostrum. We are able to cut it, and then with each of these subcircuits, we send it to everywhere else. With the ACC partition, with the GPUs, is easy because they are connected. But with the Mare Nostrum ONO, right now they are not connected. They are different clusters, even though in the future that's going to change. But the good thing, they are different clusters, but they have this shared disk, file system, which means they share the file system. And we were able to communicate with these two clusters through the file system. Then we have the second constraint, that is that Mare Nostrum cannot connect to the outside, like cannot connect to internet. So we couldn't send the IBM cloud request or like send the execution of the subcircuits from inside the Mare Nostrum. So we had to send back these subcircuits to the user, and internally, like that's all done by the Qdislib, like the user doesn't have to do anything. It's sent to the IBM cloud, and then we did we tried in a Marrakesh GPU, and with all that, then everything is regrouped together in the general purpose partition and get back to the user with a final output. Okay. Okay, these were some results that we obtained and that we presented in the paper. I'm going to focus first on the right side. We had the circuit simulation with cuts, what we already saw, comparing with executing the whole circuit in an IBM Cloud QPU. As we saw, obviously, executing the whole circuit in a QPU is much faster. Knowing that this comes with other problems like errors or like other things inherent from quantum computers, but are faster than executing, like simulating classically. But the good thing, and as we can see in both examples, is that as we increase, and mentioned before, as we increase the number of nodes that we use for GPU and CPU, we are able to kind of match this time used for the QPU, cutting the circuits, creating smaller subcircuits, and then recombining. Like, we are able to match these times, increasing the number of resources given to the application. So there was something notably that we saw and we wanted to mention, and it appears in the paper, because matching this time from a QPU is really, really good too. And finally, this table summarizes a little bit all type of experiments we tried to kind of do the proof of concept of these hybrid executions. I just highlighted the ones that used all the resources, CPUs, GPUs, QPUs, from Mare Nostrum on-site and cloud QPUs. Basically, there was kind of like to do the proof of concept that this can be done, and that we did it. And that actually, in this case, our policy to decide where to send each part of the subcircuits was basically the GPUs, all the circuits that were bigger than 18 qubits were sent to the GPUs. All the subcircuits that were smaller or equal to 5 qubits were sent to the QPUs because of the Mare Nostrum on a chip constraint, and were offloaded like in between both QPUs were offloaded like by half, and half of them were sent to the on-site QPU, and then other one to the IBM cloud QPU. And the other subcircuits were sent to the CPU to show this concept of using a completely hybrid execution. Okay, that was everything related to explanation of the Qdislib, but within the paper. And now I want to show you the examples that I have. Let me see. Okay, I think I have to stop sharing. I'll and share it again because I have another right here. Okay, so now you have to see this is the read the docs, the documentation of our library. You'll see here a lot of information. Like, if you wanna see how it works or like anything, we already posted the documentation, and we have also the GitHub here. I added last week a few notebooks so you can see. And so here is kind of a Hello World notebook for the library. And first we start, like, I wanted to do this live, but I had some technical problems with my computer, and I'll show it like this. But this is actually a notebook, like a Jupyter notebook that you can download and try it locally or where you want to do it. But I'm sorry, I cannot run it and like right now. But it's the same. You'll see the same results. So here we start with a notebook. We have this interactive PyCOMPSS that is aimed to run in a Jupyter notebook. We start importing these interactive PyCOMPSS and then starting it with this command. We see that the PyCOMPSS interactive is open, and we can start using it. And all our computations are going to be parallelized. Then we import the required modules. Here we have Matplotlib, NumPy, Qibo. I also set the backend of Qibo to be NumPy. And the most important thing, we import the Qdislib, and in this case, that's Qd, to have it right in the notebook. Our next step is to define the main circuit. Here I defined a random circuit, 10 qubits with multiple 2-qubit gates. And then we can go to experiment with the gate cutting. We have the circuit already defined here. And the first important step is to find one cut for this circuit. We call the QD find cut function. We pass the circuit. and it finds us the best cut possible in this case. Here, if we go up, we see this it's a Control Z as Control Z, and number 2. That means if we go up, here it's easier to see because it's 1 and 2. We're cutting this Control Z, and if you go up, the numbers are the numbers that are as we define each gate. So it will be 1 and 2. We're cutting this specific gate. And here, if we follow, like if we cut this gate and we cut it in the middle, if we follow how the circuits after the cut states, we'll see that we're creating subcircuits of 5 qubits each one. So kind of we're splitting these 10 qubits into the multiple 5 qubits subcircuits. Going back here, we already have the cut. So now easy as doing QD, gate cutting, circuit, the cut, and we get the reconstruction. I'm sorry, here it doesn't show, like if you put verbose through, it's not here. You'll see how it calculates every expected value of each subcircuit and then combines it together. It's not here, but I'll show you now when we go down. There's another example. And this is the reconstruction of the initial 10 qubit circuit. Going down, we have the same example for wire cutting, kind of the same. We have the circuit we call fine cut. In this case, we force gate cut false, which it's going to only find wire cutting, like wire cuts. Here we have the tuple between like the wire that's going to cut like between two gates. And do the same reconstruction equals QD wire cutting, the circuit and the cut, and we are able to get the reconstruction. Okay, and you're going to say how we know this is a right expectation value. We also have this exact expected value that is using what Qibo already has defined. We integrated it in our own function. It's called analytical solution. You pass the observable. Also, I didn't mention every time you can also enforce an observable, like specific observable. If I don't put any specific one, it means the library assumes you're using Z. So all the observables are like Z. And here we see that the analytic value is 0, and these ones are pretty close to 0. So the algorithm is doing it. It's doing it right. We have another functions that I think it can be interesting for a lot of people outside just doing this parallelized algorithm. That is, I want to get the independent subcircuits. Like I want to get each of them individually. We have a function for that. Kind of the same. We have the circuit, we find the cut, and we pass it to a function called gate cutting subcircuits. We say which we have the circuit, the cut, and we mention what quantum software we're gonna get back the circuits on. And here we have a for loop to print them. Basically, for a gate cut, for only one gate cut, we're supposed to get 6 combinations, and each combination has 2 parts, so it will be 12 subcircuits. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 subcircuits. So the user can receive, like get them individually and then manage to execute them as they want. And now when it comes the last part of this second functions that we have, that is, okay, I did what you told me. I got the subcircuits individually. Now I can do the expected value as I want. Here it's like an internal function that we had, but the user could run it as they want, like any type of execution, simulation, and QPU, whatever they want. They get the result in a list, and when having these results in a list, you can put it back in a gate cutting subcircuit reconstruction with the results, the number of cuts that the the user applied at the beginning, and is able to return the expected value true. So this is not the first option for the Qdislib, to say it like this. Like the main option is to do the whole workflow internally. But we gave the option if people wanted to do the execution of subcircuits in a different way, that they could do it. Here we have the same for wire cutting. We have the option to do wire cutting subcircuits. In this case, we specified Qibo. We get the subcircuits. In this case, it's 8 per 2, 16. All the subcircuits here. And then we have the same function to reconstruct it. We have the result in a list. We put the list back into the wire cutting subcircuit reconstruction, number of cuts, and we are able to get the reconstruction value. Once we're done, and we do the shutting down PyCOMPSS, is this comment here. We make sure all the elements, all the are synchronized, are retrieved, so we don't have anything like lost. And finally, we can print the complete task graph. That here is going to be really big because we run so many things, but I can explain a little bit. This first big graph here is doing gate cutting. As I mentioned before, I had 1, 2, 3, 4, 5, 6, because every time I do gate cutting, I do 6 combinations, and all the process of doing the workflow. Here is a little bit bigger, this one in the middle, because it's wire cutting and it's 8 combinations, but exactly the same. If we go down here, they're like a little bit shorter in depth. That's because this one is to generate the subcircuits. It's a little bit shorter. Here is when we generated all the like individual subcircuits for the user. Here we executed it, but in a separate cell, like in a separate process. And in the yellow ones is when we recombine the results to get the original circuit expected value. Same for here, subcircuit reconstruction. Sorry, subcircuit generation for wire cutting. The purples executing the wire cutting, and the darker purple to recombine the results and obtain the initial value. And that's all for my side. So yeah, I hope you enjoyed it. And anything, yeah, any questions or anything, any feedback, it's welcome.
Okay, thank you so much, Mark. I think we have time for a couple of questions. So is there any questions in the audience? I think you can type it in the chat and we can read it. In the meantime, maybe we'll start with a question, which is, could you maybe explain a little bit better why do you need this graph algorithm? So what are they doing, each of them? It's all these different methods.
So basically, we wanted to have a function that was able to give the user these cuts, like without thinking manually where I wanted to cut. And one of the problems we faced is that there are actually so many possibilities to cut a circuit. Like there are like probably infinite ways to cut a circuit, and that is very it's hard and like computational. And we wanted to find an easy way to do it. And since graph algorithms, like they're like really good graph algorithms that allows you to partitionate graphs, and since we already were converting circuits to graphs, we thought that it was probably like the best way to go using graph algorithms. Now, why we chose those 4? Basically because they gave us these multiple like different ways to find partitions. Like one was focusing on finding like the edge centrality. The other one was specific for meshes. So these multiple ways to cut gave us different results. And then we could apply this minimum loss function. But also these were like 4 that we thought that would work really good for us. But since it's all parallelized, it can be open to many, many more. Like we could have like, instead of 4, like having like 20, and have like the 20 best like 20 graph algorithms that can find these cuts. And if there's no like one that is like very, very long to like compute, they could run in parallel, and would give us like even more options to pick.
Okay. We have a question from the chat from Vicenzo de Mayo. For your weighted approach, did you consider to apply instead of multi-objective optimization approach, like having a Pareto front and select among multiple solutions?
Actually, I think no, we didn't consider that option. If it's what I'm if what I understand, our first approach didn't like result in a good result. Was like trying to do all the combinations and kind of like try to prune this or like, since you have like so many possibilities, you have kind of like a tree of like all the possible combinations that we try to prune this tree to get the best, but it kept like taking so long. But we didn't try this multi-objective optimization. I don't know much about it, but this function about like this find cut function is something that it is supposed to be improving the future. Like we want to work in that like very much and have like this much better optimization function. But it's something that we can take in account and try to see if can work in our case.
Okay. I think we have a question, but it's not related with Mark can answer. So yes, the redshift is going to be replaced by 20 qubits at the end of this year, and I was trying to find a web page where we can upload of the information. So I will share it as soon as I have it. So maybe I have a very last question for Mar, if there are no more questions from the audience, which is if you can explain a little bit more this weight. So this weight loss function, each component, what does they do? For instance, what's the difference between maximum components and maximum? Yeah.
So basically, we wanted the user to be able to specify as much as possible. The first one is easy, like maximum number of cuts. Like the user can say, I cannot afford having more than 3 cuts because the number of subcircuits it increases like really big. This is very simple and it's very useful for the user. Then we have these maximum components that is a little bit more tricky, but basically it's based that just one cut in principle, it cuts the circuit in like two components. However, there's times that a specific cut, because of the circuit's topology or like how the structure it has, only like one cut, it's allowed to create more than 2 components. It can be 3, 4, whatever, because of the structure of the graph. And that's something that it can be good, but at the same time, the granularity of the subcircuits, it's very small, and maybe the user is not interested in. So that's something that, in this case, the loss function can also be put as a restriction, like the maximum number of component generated. And finally, if I'm not wrong, it's the minimum qubits. Basically, we're trying to find those partitions that give us then the subcircuits with the minimum number of qubits. Ben, you're muted, Malva.
Thanks. Yeah. Do we have time for more questions, Javier?
Yes. Yeah, we have a couple of minutes.
So
there are, in the chat.
From the chat, from Emil Dimitrov, if I understood correctly, the time shown were for the simulation of the quantum circuit after they were cut. What is the overhead of computing the cuts and recombine the results?
So wait, no, maybe I didn't mention that. The time in the graph and like everything I mentioned is the time that the whole workflow takes. Like since I actually call the function with a circuit, like all the transformation to graph, the combination, the execution, and recombination, all this workflow is the time that we show. And your question, overhead of the overhead, yes. So the overhead at the end is as much like every time you add more cuts, like instead of 4, you apply 5, 6, 7. That's a lot of like much more subcircuits that you have to handle, that you have to execute, that you have to recombine. So what we saw that added more overhead was increasing the number of cuts, even more than the depth of the circuit or like the complexity of the circuit. Like adding more cuts, it was always much more added much more overhead, and it was computational harder.
And yeah, final question, quick questions from Alfonso Garballo. You mentioned the importance of resource allocation between CPUs and GPUs based on circuit complexity. Could you elaborate on the criteria or metrics you use to determine when to switch from CPUs to GPUs for optimal performance?
Yes. So this is a very good question, because actually we kind of like ask ourselves like what could be the policy right now to make it simple. We had a policy that we said, okay, if the circuits are bigger than 18 qubits, I think it was, yes, we were sending it to the GPU, and if they were smaller, either bigger than 18 to the GPU, and smaller to the CPU or QPU, depending on other specific things. But that's something that we want to kind of like extend and even give the user the opportunity to decide how to handle this. Not like right now that the user can handle it putting a threshold for the qubits, but maybe we can manage to internally to decide where to send what and in where, depending on how that machine is in that moment and how many resources we have available. So that's something that in the future we're going to increase internally to have a better runtime that is able to send it not only for a specific case like for qubits, but for other external things, to say it like this.
Okay, a very last question from Jorge Vázquez Pérez. Did you compare the time taken with the uncut execution of the circuit?
So did you compare the time? So I don't know if I'm understanding it right, but so what we compare in the last few slides that I was showing was what was a comparison between sending the whole circuit to the IBM cloud, and since they have like 156 qubits, we were able to send like big qubits there, and comparing it to the time taken for us to sending it to Mare Nostrum with the cuts, the recombination, the execution of subcircuits. And what we saw was that sending it to the IBM cloud was much faster. But however, as we increased up to 64 nodes in Mare Nostrum, we were able to kind of match those times pretty close, even though obviously the resources were more bigger. But that was like pretty good for us, because even though classically it's supposed to take more time, we were able to match these like QPU times from IBM.
Okay, thank you so much, Mar. I think that's all at the moment. Of course, if any of you have more questions, you can contact her, and I encourage you to check the documentation and all the examples. And that's it. So see you in the next quantum seminar, Quantum Spain seminar. Thanks for coming.
Thank you.
And thanks, Mar, again.
Thank you so much.